In this video, I want to analyze the telemetry data available from both live feeds. So really, how does the trajectory of the orbit of the New Glenn and the Starship differ? The most noticeable aspect is how slow the New Glenn lifted off the pad. The key differences that are clearly evident is that the New Glenn booster burns longer than the Super Heavy, 190 seconds compared with about 155 seconds. Stage separation is at a higher altitude and a much higher velocity. Getting back to the graphs, for both booster, we see that the classic track of slow acceleration, which is the gradient on a velocity time graph, steadily increases until MECO and stage separation. Then a similar trend happens for the second stage. This occurs as the mass of the combined ship and booster declines as fuel is burnt, while the thrust slightly increases as the ship boosters climb out of the atmosphere into the vacuum of space. For the second stages, it's clear to see that the Methalox Starship is much quicker to orbit and has much more thrust to weight ratio than the Hydrolox burning New Glenn upper stage. Although the New Glenn upper stage has more powerful Hydrolox engines than the majority of Hydrolox upper stage rockets. Regarding acceleration, it's much clearer if we look at this acceleration time graph for the first 240 seconds. According to my reading of the telemetry data, the New Glenn has initial thrust to weight ratio, or an initial acceleration of between 1 to 2 meters per second squared. This equates to an initial thrust to weight ratio of about 1.1 to 1.2. In comparison, the Super Heavy starts at about 1.4 to 1.5 thrust to weight ratio. After about a minute, the accelerations are much closer, and after 2 minutes, the New Glenn powers on to about 26 meters per second squared, compared to the maximum for the Super Heavy of about 15 or 16 meters per second squared. This late rapid increase in acceleration explains how the New Glenn booster stages at a higher velocity and altitude. But why is this so? I'd like to offer 3 possibilities. First, the ratio of dry mass to wet mass is much less for New Glenn due to using aluminium and aluminium-lithium compounds rather than much denser stainless steel on the Super Heavy. Also, the second stage is not reusable, so the dry mass is even less due to not needing flaps or a heat shield. Second, the New Glenn booster lands on a drone ship, meaning it needs a much shorter entry burn compared with the over 1 minute boost back burn that the Super Heavy required to get back to launch site, meaning the fuel reserved for recovery is less. Finally, the proportions of the first stage to second stage for both rockets appear similar. However, there is one real difference. New Glenn uses Hydrolox fuel. Now, although this leads to less energy available in the upper stage of the New Glenn, made of hydrogen rather than similar tanks with Methalox, this is somewhat over-mitigated by higher efficiency. What it means, though, is that the thrust-to-weight ratio is much higher for New Glenn as the booster fuel starts to run out, as it does at about 2 minutes, as it is lifting far less mass as a proportion of the total mass of the rocket compared with Super Heavy. Now, this is my take on the telemetry. If you agree, or even if you disagree, drop in a comment and hit the like and subscribe button for an upcoming video on whether HLS can realistically replace both SLS and Orion.